This is the last section of the differentiation chapter, and this is called rates of change, and this is going to allow us to solve problems using mainly the chain rule. Now the chain rule you could think of as basically having lots of things like dy dx and maybe I don't know, dA dy for example, and treating these like fractions. So treating like fractions and multiplying them together to get new things which are sort of d something over d something. So for example, if I were to do this dy dx, let's say I work that out, and a question also worked out dA dy. If I multiply those together, then I get dA dx, and that may be something that I need to work out. So when you have questions like this, you want to start by differentiating to get your expressions, and then once you've differentiated, you want to use the chain rule, and that basically means like multiplying things together. So multiplying, I'll call them fractions, they're not really fractions, but you know what I mean, dy dx, dA dy, those types of things, multiplying the fractions to create a new expression. And we cannot solve all sorts of problems by using this approach. So here we have a question to do with the area of a circle. So we've got the formula for an area of a circle, and it says the rate of change of its radius given in centimeters per second. Now I might refer to this later. This is going to be useful, these units here. Is given by dr dt equals 5, and it says we need to find dA dt. So whatever we finish with, we want to find dA dt, and then we want to substitute 3 into that and work out what it is. In other words, what we want to work out is what's the change in the area over time when the radius is 3. So I'll say that again. What's the change in the area over time when the radius is 3? And what we've got here is the change in radius over time is 5. Yeah, so you can actually change these, you know, think of them like sentences. So let's start with what we've got. We've got the area is pi r squared. Now remember, pi is a constant, it's a number. Yeah, it's a number like 3.1 or 3.14, it's a number. Now what we're going to do, the reason I mention is it a number, is because we're going to differentiate this, and it's going to be dA dr, because r is what's changing. There may be other letters in there, this just has pi, but r is the thing that's changing. So think of this like, I don't know, if that was 3r squared, what would that become? Well, you would multiply the number here by 2, and you take 1 away from the power. So you think of it just like normal. This becomes 2 pi r, which is very interesting, that when you differentiate the area of a circle, you get the circumference of a circle. That's interesting. So now I've got dA dr, and I've been given dr dt is 5. Okay, so that was given in the question, and I need to find dA dt. Now this is when we think of these like fractions. There's an a up here and there's a t down here. This has got a dr at the bottom, that's got a dr at the top. They're going to cancel out if I multiply them together. So dA dt is equal to dA dr times by dr dt. Yeah, can you see that algebraically that works? Now dA dr is 2 pi r, dr dt is 5, So what does that mean? That means that dA dt is 10 pi r, which is actually what we wanted. We wanted to work out what dA dt is. Now all we need to do is substitute r in, so we can say at r equals 3, dA dt equals 10 times pi times 3. So it's going to be exactly 30 pi. So there we go. That's it. That's a simple example, but that's basically how it works. Right, there's another one here. We've got the volume of a hemisphere V is this. Now when I do these questions, I write out what I've been given, because it's easy to lose what you've got. So I've been given that. I've been given a formula for the surface area, pi r squared plus 2 pi r squared. Oh well, that's just 3 pi r squared. So let's just write that down. There's no point writing that out separately. 3 pi r squared. And we've been given that dv dt is 6. Now, oh right, I remember in the last example I did talk about these units here. Given that the rate of increase of the volume is centimeters cubed per second. Now this can help you with the units you have here. Centimeters cubed volume per second time. Volume over time, volume over time. The units match. And sometimes you're not given this expression, you need to work it out. It's going to be d something over d something, you don't know what it is. But if you look at the units, that can help you. This is a volume, this is a time, second, so it's volume over time. So that can help you if you don't know what these units are. And what I need to do, find the rate of increase of the surface area, so I need to find ds dt. So what I'm going to do is I'm going to differentiate what I've got. R is the thing that's changing. So we're going to differentiate with respect to r. Now remember, pi is a variable. So if I do 2/3 pi r cubed times that by 3, I get 2 pi r squared. That's dv dr. This is going to be ds dr, and this becomes 6 pi r, and we've got this dv dt. Now all I need to do now is to see, right, how can I string all of those three things together to get ds dt? Well, I want s at the top, and the expression that has s at the top, or that has s in it at all, is this. So I'm going to do ds dr. Now my final expression doesn't have r in it. Yeah, I don't want r there, so I want to cancel this out, and I can do that by using the reciprocal of this. If I make this dr dv, that will cancel out the dr. So the next thing I'm going to write down is dr dv. Now this is just the reciprocal of the dv dr, and it will just be the reciprocal of this. It'll be 1 over 2 pi r squared. Now how am I doing? So that's going to cancel out. So I've got ds at the top, dv at the bottom. I want to get rid of that dv at the bottom and replace it with dt, so I can just put this in. So the next one is going to be dv dt. So when that all gets multiplied out, that's going to cancel. That will give me ds dt. So now I'll just replace them with the actual expressions that I've got there. So ds dr is 6 pi r. Oops, don't need to put times in. So 6 pi r times by dr dv, which is the reciprocal of 2 pi r squared. So that's 1 over 2 pi r squared, times by dv dt. which is 6. So let's simplify that. So what will happen is that pi and that pi will cancel out. The 6 and the 3 will cancel down, so that becomes 3. That r will cancel out with one of the r's there. Now what does that leave? That just leaves 18 as a final answer, I think there. Yeah, everything else cancels out, so just 3 times 6, 18. Oh, and the r here, this r hasn't cancelled out completely, it's just the power. So sorry, 18 over r is going to be my final answer. Now if I needed some units, what am I working out? The surface area over time. So the units would be an area over time. Yeah, so they're the units. It's an area over time, surface area over time, area over time. There we go. Okay, let's have a look at this one. The decay of radioactive particles. So decay is always going to be a negative in my equation. The rate at which the particles decay is proportional. Now in maths, whenever we have anything that's proportional, we use the letter K to the number of particles remaining. Write down a differential equation for the rate of change in the number of particles. So we don't need to actually solve anything. We just need to write down a differential equation. Now we're not given any variables here. What's important is the number of particles, the number of radioactive particles. So we need to assign a letter for it. So let's say the number of radioactive particles is, let's use P to represent the number of radioactive particles, and we'll use T for time. That makes sense. So now let's transfer this or work this out as a differential equation. So the first bit here, in the decay of radioactive particles, so how would we look at or work out the decay of radioactive particles? Well, we'd look at the change in the number of radioactive particles over the change in time. So think about what it is as a sentence: the change in the number of radioactive particles over the change in time. And how is that worked out? Well, it says it's a decay, so we're going to need a negative. It said it's proportional, so we're going to need K. And what's it proportional to? The number of particles remaining. And what does that equal? P. Yeah, P is the number of particles remaining. Yeah, and that's it basically for this. I mean, we could have started off here by using one of those little fish signs, alpha, and then written it as K, but that's fine. It's a nice easy one, nice short question. Newton's law of cooling. Another one with no letters, so let's work out what we've got. Newton's law of cooling, so it's the rate of loss of temperature. Okay, so negative, we've got a loss of temperature. Let's use T to stand for temperature, is proportional. Okay, so there's going to be a K there, proportional to the excess temperature of the body over its surrounding. This is new. Excess temperature of the body over its surroundings. Write an equation that expresses this law. Now, because we're looking at temperature, I shouldn't really use T to represent temperature because we're going to be using T for time. So is it Fahrenheit or Celsius? Doesn't say. So let's use C for Celsius. Yeah, so we're going to use the temperature of that body. Now it says it's we need to work out this excess temperature of the body of the surroundings. So we actually need a letter to use for the temperature of the surroundings, because that's going to be fixed. That's not going to change. So let's use C with a little s to stand for the temperature of the surroundings. So if you were doing this in exam, then you want to say things like write down that, you know, for the temperature, so you would say let temperature equal C, let temperature of surroundings. So let the examiner know what these letters are standing for. Temperature of surroundings, CS, so that they know, and then obviously your time is going to be T. So let's now write a differential equation for this. So we want the change in temperature over the change in time. How do we find the change in temperature over time? Well, it's a loss of temperature, so it's a negative. It says it's proportional, okay, and it says it's proportional to the excess temperature of the body over its surroundings. Right, how are you going to work out that excess temperature? Well, you want the temperature of the body, the object itself, and you want to take away the temperature of the surroundings, and that's it. That's all we need to do. So when you do these questions, talk it through in your head, you know, or even write a sentence down. All you're doing is translating from a sentence into some maths, and it should almost read the same way as you read that. The change in temperature over time is decreasing at a rate which is proportional to the difference, basically, or the, yeah, not difference, but the excess of the temperature of the object over its surroundings. And that's it. Talk it through in your head, maybe even write down a sentence, underline the questions on the page, write down what letters are standing for what in your question. Snowman. So the head of a snowman, radius is R, it loses volume by evaporation. So as soon as I see loses, I'm going to have a negative somewhere. Rate which is proportional, so there's going to be a K there, proportional to its surface area. Okay, so there's going to be some area there. Assuming that the head is spherical, that and then we're given the volume of a sphere. That's nice of them. And here's the surface area. Write down a differential equation, so that's going to be d something over d something. And what is it going to be? The rate of change of the radius of the snowman's head. So that's going to be the rate of change of the radius over time. So this is what we want to find. dr dt, the change in radius over time. Now that should be big R, because the question uses big R for radius. That's what we want to get to. So let's see what we have. The volume of the sphere. So the volume, let's go over here, is 4/3 pi r cubed. So I'll write that down. The surface area, so we'll use A for area, is 4 pi r squared. Now if I differentiate this here, the volume, I'll get dV dr, and 4/3 times 3 will give me 4 pi r squared, which is going to be useful because I've got dr here, and I maybe can do the reciprocal of that. That can start me off. But there's not much point in differentiating this, because this is going to give me dA dr, and I don't think I'm going to get much further. But I do notice that dV dr actually equals that. They're both the same. So let me write down actually here as well that it equals A. Yeah. So let's see here. So dr dt, well, I can work out what dr dv is. Yeah, that's just going to be the reciprocal. I'll just put the flip of dv dr. So I've got that bit. Now for this to work out, I actually need to multiply by dv dt. Now I have dr dv. Let's write that down first of all. So that's going to be 1 over 4 pi r squared. But I don't have dv dt. I don't have an equation that I can differentiate to get dv dt. But what does it say in the question? It does tell us something about dv dt at the start here. The header of a snowman radius r loses volume, right? So minus, it loses its volume by evaporation at a rate which is proportional to the surface area. So I can write down dv dt from the sentence that's there as minus ka. Now, do you remember we said that this is the same as a? So if I put a there, I'm going to get some stuff that cancels out. So I could write that as 1 over a times by minus ka, and then I just finish with negative k. That's it. So that's the differential equation. You don't need to solve it. So dr dt works out just to be negative k. So it was part of that was doing some differentiation to get dv dr, which we flipped to make dr dv, and then the other bit, the dv dt bit, we got from actually the first sentence that the change in volume over time is decreasing by a rate which is proportional to the surface area. So this came from the first sentence. You should now be able to do exercise 9J on pages 263 to 264 of the textbook, and then from there you can do the mixed exercise, and that's the differentiation chapter complete.